Hello everybody and welcome to 6th lecture of MHM 42780. In our previous session we talked about how to calculate radiation heat transfer between surfaces based on view factor. We also talked about resistant network and how we can use it to simply understand what is happening in radiation. In this lecture, we are going to continue to talk about the same concept, maybe a little bit more complicated applications, and see how we can extend the knowledge that we gain. So every day we are learning new things and we are extending and we are applying what we learn to new examples, more complicated ones. Okay, in some engineering application to reduce the net radiation heat transfer between two surfaces, a radiation shield will place between two surfaces, as you can see here. So those radiation shields are constructed from low emissivity materials. If we find a radiation resistant network between surface 1 and 2, it will be so easy to find Q.1 to 2. So first let's start with the simple two parallel plates and the radiation resistant network associated with it. Okay, and after that we can extend it to the other things and see what we can get. Okay, as you can see here, we have two parallel plates and the radiation resistant network associated with it is showing here. So it's so simple. We have two surface resistances. Why surface resistances? Because we said that we have two surfaces with emissivities. So we need to take into consideration the property of the surface. We have two surface resistances and one space resistance. We talked about it. EB1 is emissive power of black body at the temperature of surface 1. J1 is a total radiation energy leaving surface 1. J2 is radiation leaving the entire surface 1 that strikes surface 2. And EB2 is the emissive power of black body at the temperature of surface 2. So how about two parallel plates with a radiation shield between them? Okay, let's see. So there are two parallel plates, but we have one radiation shield between them this time. Okay, let's see how we can get the resistant network. So do you agree with me that we have four surface resistances? Why? Because we have four different emissivities. We have emissivity for surface 1, we have emissivity for surface 2, we have emissivity for the right hand side of the shield and left hand side of the shield. Do you agree with me? Okay. Those four surface resistances. In order to connect these, we need two space resistances, as you can see. So now we have the network consists of 6 series resistance. So how we can find the resistances? As you can see here, the surface resistances is easy. 1 minus epsilon associated to that surface divided by emissivity multiplied by A. We apply the same concept for all those four surface resistances, and we know that the space resistances are related to view factor. So we have it here as well. Okay, it's very simple, but at the same time, if you don't give enough attention to it, you might miss something or make a mistake. Okay, this is the resisting network, and if you want to have it more clear, you can see here sorry, it's okay. Now here you can see we have all those four surface resistances. Why? Because we have four radiosity active surfaces, and I said in order to connect those two surfaces together we need space resistances. Okay, this is the final network or resistant network for. But let's solve one example and see how we can use those like equations or like a complicated networks into one example and see how does it work. We can see here that a tin aluminum radiation sheet with an emissivity of 0.5 on both sides. So in this case, for this example, top side and the bottom side of the shield they have the same emissivity. We have two very large parallel plates. We have their temperature. T1 is 900 Kelvin, T2 is 650. We have their emissivities for each of those surfaces. And now the question is asking us to determine the net rate of radiation heat transfer between the two plates per unit surface area compared in two different conditions, with shield or without shield. So what was the reason why we used the shield? To reduce the radiation between those two surfaces. So we are expecting that the radiation between two surfaces be much bigger compared in the case of no shield compared to with one shield. Okay, but let's just like solve it and see. Okay, in this case, so it's asking for net rate of radiation heat transfer between the two plates. So first we are saying that okay, Q dot 1 to 2, it's what is asking, but at the same time is saying that per unit surface area. Per unit surface area, you can just write it down as like the equation will be sigma T1 to the power 4 minus T2 1 minus epsilon 1 epsilon 2. Okay, so it's very simple, but at the same time we have all the numbers. We have the Stefan Boltzmann constant, we have temperature, we have emissivity of the surface 1, we have emissivity of surface 2, and the number it's 12,035.36 watt a square meter. But now let's calculate it when we are having the shield, and after that compare these two numbers. So let's write it down here. You want to A but no shield. Okay, we keep it. Now let's calculate with shield. Okay, so first let's find the resistant network. It's the same as to the slide before, but just like I'm right again. So we have four basically surfaces with four emissivities. So we are going to have four surface resistances, R1, R2, R31, R32. In order to connect those two areas, we need two space resistance. So the space resistance is R31 and here R32. This point EB1, we have the surface temperature. EB2, again surface temperature. 2, J1, J31, J3, 2. Okay, now if we use the same concept of Q dot 1 to 2 is equal to running force divided by resisting force. So what we have will be EB1 minus EB2 divided by R equivalent. But for Q dot 1 to 2 divided by A, we will have this equation. So it's EB1 minus EB2. It's 1 minus epsilon 1 plus 1 plus 1 minus epsilon 3 1 epsilon 3 1 plus 1 minus epsilon 3 2 epsilon 3 2 plus 1 minus epsilon 2 epsilon 2 and plus 1. Okay, now if we have all the numbers, we have all the emissivities, we have we know that this is sigma T1 to the power of 4 minus T2 to the power of 4. So the number will be, I have calculated, is 1856.0.4 watt a square meter. So Q dot 1 to 2 divided by A and shield. 1 shield. 1 shield. So let's compare these two numbers. The number that we are having here and the number that we get from the previous one here. If we compare these two, we are going to have Q dot 1 to 2, 1 shield divided by Q dot 1 to 2, no shield, around 1/6. So now you can see why they use the radiation shield. Decreases the radiation significantly. Okay, but the other thing is like it looks very simple. Is there any like easier way to do it? Yes, of course. There is a table 3.3. I just showed you previously. It's for some very standard or famous two surface arrangements. You can use those equations inside the textbook. You don't need to do anything, just you can refer it that I'm using this equation, for example 13.38 or 13.39 from table 13.8, and you will be fine. But let's see how we can use this one, because it is for just two large parallel plates. But how we can use this one when we are dealing with radiation shield? Okay, so when we are dealing with radiation shield, what we can do is, it's very simple. In this case, we can say Q dot 1 to 2 is equal to, the running force will stay the same, so A sigma T1 to the power of 4 minus T2 to the power of 4. But here we can write it like that: 1 divided by epsilon 1 plus 1 divided by epsilon 2 minus 1 plus 1 epsilon 3 1 plus 1 epsilon 3 2 minus 1. So it was for one shield. How about n shield? So q dot 1 to 2 n shield. Again the same, the running force stays the same. Sigma T1 to the power of 4 minus T2 to the power of 4. And in this case it will be 1 epsilon 2 minus 1 plus 1 epsilon 3 1 plus 1 epsilon 3 2 minus 1. Continue until the last shield n1 n2 minus 1. Okay, so it's very simple. You can use those tables, so don't worry about it. You don't have to calculate all those correlation at any time, like find it. Now it's time to study three surface enclosures. This picture shows an enclosure consists of three opaque, diffuse, and gray surfaces with uniform temperatures of T1, T2, T3, and we also know all the emissivities. As I told you before, we are interested in finding a unique solution for unknown surface temperatures or heat transfer. And if you remember, I told you that we have two different options. We can either do the direct calculation by using computer, or we can use the radiation resistant network or resistant network. We can use both words. So to find the resistant network in this case, so is it fair to say that we have three different surfaces, so we are going to have three different surface resistances? Yeah, I think so, because we use the same mentality. We have three surfaces, three different properties, because we are dealing with the surface with different emissivity, so we have three surface resistances. In order to connect these three surfaces together, we also need three space resistances. So that's it. That, as you can see, this is our resistant network when we are dealing with the enclosure consists of three surfaces. All three endpoints, there are emissive powers and known because of surface temperatures are known. So since surface areas and emissivities are known, we need just to find the radiosities of J1, J2 and J3, and after that we will be set. Okay, so here we need to use the concept of electrical engineering to be able to find the radiosity. For electrical engineering, the algebraic sum of the current at each node must be 0. By implementing the same concept into our network, we have three equations. But let's see how we can get those equations. First, we are going to start from here. As you can see, we start from point A, we go. This is our first equation. We start from point 2, and this is our equation. And after that, we start from point 3 or surface 3, and this is our equation. So those are the three equations that I was speaking about. By having these three equations, we will be able to find all the radiosities. Yeah, that's all the three equations. Okay, but there is another thing that we need to take into consideration. The assumption of radiating or insulated surface is common in many applications. So this surface is characterized by zero or net radiation transfer. So for example, it is acceptable for real surfaces that are well insulated on one side and having negligible convection effects on the opposite sides. In this case, we are assuming that surface R in this picture is assumed to be well insulated and convection effects are assumed to be negligible. By knowing that, the resistance RR will be out of the network. You see here? So those just like green areas are inside and the red is outside the network. Why is that? Do you know? So RR here is out of the network and the net radiation transfer from surface 1 must be equal to the net radiation transfer to surface 2. So since RR is out of the network, it will be very simple, like a series parallel arrangement, and I can say that here Q dot 1 is equal to EB1 minus EB2 R1 plus R and plus R2. So R1, R2 and R equivalent for this area. How we calculate that one? So R length is equal to 1 R2 plus 1 R1 R plus R2R minus 1. Okay, so that's how does it work. And if we look at this slide, we can just see it if we just use those two equations. Why we didn't use the third one? Because we said that in this case, because it's well insulated, EB3 is equal to 3. So this is 0. When it's 0, these two are equal. When they are equal, these two are the same. So as you can see, it makes our life much easier to calculate. But let's solve one example together and see how we can implement these concepts into practice. We have a paint baking oven, consists of a long triangular duct in which a heated surface is maintained at 1200 Kelvin. Another surface is insulated. Painted panels which are maintained at 500 Kelvin. Triangle, we have the size. The emissivity, we have the emissivity as well. So the question is asking what is the temperature of insulated surface. Okay, so what do you think? What should be our first approach? What we are supposed to do? Do you have any idea of what we are going to do? So Let's start with first finding the network. Okay, let's find the network first. So network, it will be like this. So okay, and one here. So this is Q.1, this is EB2, R2, J2, EB1, R1, J1, EB3, J3, R3, R1, 3, and R2, 3. Okay, so 1, 2, 3 surface resistances and 1, 2, 3 space resistances. The question is saying that surface 3 is well insulated and it's radiating surface. So R3 is or going towards the infinity, and Q.3 is equal to 0. Now for this example, I suggest you do something like that. What we have in information, what we would like to find, or what we need to find. So what we know that convection is negligible. We also know that the surface 3 is re-radiating and well insulated. What we need to find is the rate at which heat must supplied per unit length of the duct. This is the first A. And B, what we need to find is temperature of surface 3. So T3, we need to find T3. Okay, let's start from, as we said, this will go out. Why? Because the resistance is infinity. When the resistance is going to be that high or infinity, there is no current will be in this section of the network. So Q.1 is divided by minus Q.2. Why? Because Q.3 is equal to 0. It's EB1 minus EB2, R1 plus R plus R2. Let's go back to this one. Set it. So R2, R1, and these 3, call it R equal. Okay, so we will finally have this equation. EB1 minus EB2, R1 plus R12 from R13 plus R23 minus 1 plus R2. Okay, so R1, R2, both of them, they are surface resistances, R12, R13, and R23. All three of them are space resistances. So we just write it down. So we know that R1 is surface, so related to the surface, to the same surface resistance related to the surface, and space, so of course they are related to view factor. R3 is 1 A1 F13, and R23 is equal to 1 divided by A2 F23. Okay, so we have all those things. So but let's say how we are going to calculate those view factors, because we need to find the view factors. Okay, so view factor, know that F11 plus F12 plus F13 is equal to 1, but F11 is 0 plane, so, and from symmetry we have 1 2 is equal to 1, F13 is equal to 0.5. okay, the question is asking the rate per unit length of the duct. So Q dot 1 divided by L is equal to, driving force will stay the same, 4 minus 2 to the power of 4, it's exactly the same. But here, so instead of A, because we know that A1 is equal to A2 is equal to W by L, but because it's per length, so instead of A we just use W. So 1 minus epsilon 1 W plus 0.5 W. We are implementing the view factor as well. Plus 1 divided by 2, 0.5 W minus 1 plus 1 minus epsilon 2 W. Okay, we already have everything. We have Stefan Boltzmann constant, we have temperature T1, we have temperature T2, we have epsilon 1, we have epsilon 2, we also have W. Okay, so Q dot 1 divided by L is equal to minus Q dot 2 divided by L is equal to 36,902.71 watt per meter. So the A section is sorted, but how about section B? Is asking for us for T3. It might looks okay, it was so easy, but so most probably we can easily find the T3 as well. But let's go back to the insulated surface here. In order to find the temperature T3, so first we need to find J3. When we find J3, we can say that okay, it's insulated, so J3 is equal to EB3 and is equal to sigma T3 to the power of 4. So first we need to find G3. In order to find G3, we need to find G1 and G2. So it looks a little bit easy, but actually it's a little bit complicated. So we need to find, in order to calculate T3, we need to find J3. In order to find J3, we need to find J1 and J2. Okay, let's start from the beginning. So we can say that, okay, Q dot 1 is equal to EB1 minus J1 divided by R1. Here. So driving force in this area, just for if we write it for this area, driving force divided by resisting force. If we do the same thing, we can have Q dot 1, we calculated it. So we have this one, Q dot 1 divided by L, we just calculated, but how about Q dot 1, because it's like we don't have L. So let's see what we can do. Here J1 is EB1, am I right, minus R1 Q dot 1. So basically it's EB1 minus 1 minus epsilon 1A Q dot 1. Let's focus on this one. So EB1 minus 1 minus epsilon 1 W multiplied by L Q dot 1. The L goes here, so basically it's EB1 minus epsilon 1 W multiplied by Q dot 1 divided by L. So we have this one, we just like calculated the number. So J1 will be 8323 watt square meter. Okay, J1 was easy, we calculated it, but now we also need to find J2 in order to calculate J3, and after that, based on J3, we can find temperature of surface 3. Using the same concept, we can say that, okay, J2 is equal to EB2 minus R2 Q dot 2. So EB2 plus R2 Q dot 1. Why? Because we said that Q dot 1 is equal to minus Q dot 2. So J2 simply is equal to sigma T2 to the power of 4 plus 1 minus epsilon 2 W Q dot 1 L, which we already have it. So we have this one, we have epsilon 2, we have W, we have T2, we have Stefan Boltzmann constant. So J2 is equal to 59,043 watt a square meter. Now that we have J1 and J2, we can calculate J3 based on this correlation. So J1 minus J3 divided by 1 F13A1 is equal to J2 minus J3 1 divided by F23A2. Okay, so if we do this one, please do it yourself. I don't have enough time to do it. We can find T3 to be 1102 Kelvin. Please try it at home and see if you can get to this number. But you might ask that, is there any other way to find it? Yes, because we just talked about those three equations. You remember that? We can use the same concept to solve this problem as well. But how we can do it? Let me show you. Okay, sorry. Okay, so you remember those the three equations? Let me just write it down here. But I just need to be a little bit fast because we are going over time, but I'm sorry about it. R13. You can just use your textbook because you know that it will be an open book exam, so it's not a problem. I'm just writing it here, but you can just go to your textbook and easily write it down for exam or class test that we might have, or semester test. Plus J3 minus J2 divided by R23 is equal to 0. And the third equation was this one, R13 plus J2 minus J3, R23 plus EB3 minus J3 divided by R3 is equal to 0. So we said that, okay, point 3 is when well insulated, so this section will be 0. Why? Because 3 is equal to EB3, and that's the reason how we could find the surface temperature, the temperature of surface 3. So we have it. Let's implement everything and put it into three equations that we can solve simultaneously. So we have EB1 minus J1, 1 minus epsilon 1, epsilon 1A1 is equal to J1 minus J2, 1A1 F12 plus J1 minus J3, 1 divided by A1 F13. The second equation is EB2 minus J2, 1 minus epsilon 2, A2 is equal to J2 minus J1, 1 divided by A2 F21 plus J2 minus J3, 1 divided by A2 F23, and the third one, after removing that section, which J1 minus J3 is equal to 1 A1 F13 plus J2 minus J3, 1 divided by A2 F23 is equal to 0. So A1 is equal to A2, am I right? So we can remove A from everything. We don't need A here because they are the same. So we can remove A. We also have the epsilon, the numbers, we can put them. So no problem, epsilon 1 and epsilon 2. So what we are going to get at the end of all the simplification, it's these three equations. So we will have three equations that we need to solve in order to find the J1, J2, J3, and after that, based on that, find the temperature. So it's like 10 J1 minus J2 minus J3 is equal to 940584 minus J1 plus 3.31. J2 minus J3 is equal to 4725, and minus J1 minus J2 plus 2J3 is equal to 0. Okay, so we have these three equations. By solving these three equations simultaneously, you can use your calculator. That's the reason, because without calculator you won't be able to solve it. So by three equations simultaneously, simply you can find J1 to be 108,328, J2 is equal to 59018, and J3 is equal to 83,673. Now that we have the J3, we know that epsilon sigma then T3 is equal to sigma 4. Okay, basically that's it, and the answer, as I told you previously, it is 1102 Kelvin. Try to use the both method and see if you can get the same result. If you can't, please go back to the video and check it again and try to get it right, because when we go into the more complicated examples or question, after that you will have a problem, because it was just all about radiation. After that we are going to add convection to it, we are going to add conduction to it, so it will be a little bit more complicated. That was the end of our sixth lecture. In the next lecture we are going to talk about effect of conduction and convection as well into radiation, especially when we are going to create those kind of networks, resistance networks, and how we are going to do it. I'm trying to solve two very complicated example next lecture, and during the lecture, while I'm solving those examples, I'm going to provide you with a very good understanding how you need to do the same during the exam or semester test. But of course it's not just about exams, mostly it's about you to understand the concept and the discourse properly. Please go through your textbook, solve examples that I told you, and if you have any problem, you are more than welcome to drop me an email. But of course, as I told you, after every 3 video lectures, we are going to have some online Google Meet to discuss, and it will be an opportunity for you to ask any question that you might have. Enjoy the rest of your day, and that was the end of our 6th lecture.